By the late 1920s, Einstein and Planck, and then later on Louis de Broglie, established the duality of matter and light, where both light and matter exhibited both properties of waves and particles. The mathematics of this newly emerging quantum theory at the time was developed by them, along with the likes of Bohr, Heisenberg, Pauli, and Max Born. Then, in 1926, Erwin Schrödinger wrote down his famous Schrödinger equation, which describes these matter waves represented by the wave function psi. Through this equation, various quantum phenomena were predicted and explained. But this equation, accurate as it may be, in many cases, it breaks down. First of all, it does not account for the spin. Even though it does describe the orientation of electrons in orbitals, but it only allows for one electron per energy level, which is not the case for electrons when the spin is taken into account. Secondly, since the Schrödinger equation is just a simple kinetic plus potential energy equation, not involving any mass energy and no relativistic corrections, it cannot account for the particles approaching the speed of light. This is a big setback because the subatomic particles that we study are mostly relativistic in nature. Then, in 1928 came Paul Dirac with solutions to the problems faced by the Schrödinger equation. He combined quantum theory and special relativity to describe the behavior of an electron moving at relativistic speed with this equation, now known as the Dirac equation. This equation resolved the problems faced by Schrödinger equation. However, there were still some things that needed to be explained. When solving this equation, the energy came out to be both positive and negative, which was quite peculiar. The other thing is that the solution to this equation is a 4-element spinner. Although the first two elements represented the spin up and spin down of the electron, the other two elements were just there, which was quite puzzling to him at the time. To explain these oddities, he came up with a theoretical construct known as the Dirac sea, and his theory was known as the hole theory. He imagined that all of space in the universe is made up of negative energy electrons. Although they fill up all of space entirely, they are not something we can interact with. But when an electron jumps to positive energy, only then can we interact with the electron. As the electron moves out of the sea of negative electrons, a hole is made. This hole should be able to move in space as a particle, just as electron holes in semiconductor theory move, and can therefore be thought of as a particle itself, and we call this particle the antiparticle. Thus, the electron and its counterpart, the anti-electron, have the same mass, but their charges are opposite. These particles therefore move in space as separate particles. But when they come together and they interact, they annihilate each other to give out pure energy as photons, which therefore describes the process of pair annihilation. Dirac's model for particles and antiparticles can similarly describe the other particles in the Standard Model, leading to its extension. Dirac's model, however, only accounted for spin-half particles, which are the fermions, leaving the antiparticles of the spin-1 and spin-0 bosons unexplained. Dirac's theory was later superseded by the currently standing quantum field theory, which describes the particles as just vibrations in a quantum field, and the antiparticles are just different kinds of vibrations of the same field. So this theory can explain the antiparticles of the rest of the particles. Although the other bosons, like the photon, apart from the blue bosons, are of zero charge, so they can be considered to be their own antiparticle. The existence of these antiparticles was experimentally verified in 1932 by Carl D. Anderson while trying to determine the composition of cosmic rays in a cloud chamber. And in 1955, the antiproton and antineutron were discovered by Emilio Segri and Owen Chamberlain. We therefore have interpretations for the occurrence of negative energies, and the 4-element spinner solution that puzzled Dirac was explained by the up and down spins of the electron and its counterpart, the positron. Now that we've discussed the origin of the concept of antiparticles, let us now go into what this implies for antimatter, which is made up of these antiparticles. and how it affects physics and our daily lives. During the production of a pair of matter and antimatter, it is always implied that there should always be a one-to-one correspondence, meaning a 50-50% amount of matter and antimatter. And consequently, during the Big Bang, the amount of matter and antimatter should be equal. These equal amounts of matter and antimatter should have annihilated each other over time, leaving nothing behind, or at least show signs of a diminishing universe as we look around us. But as far as we know, this does not happen. This is one of the biggest mysteries modern physics faces today, and it has been approximated that there was one extra matter for every 1 billion matter-antimatter pairs. There are small amounts of antimatter constantly raining down on us in the form of cosmic rays. But antimatter is actually closer to us than we think. Bananas produce antimatter, releasing one positron, which is the antimatter equivalent of one electron, about every 75 minutes. This occurs because bananas contain a small amount of potassium-40, a naturally occurring isotope of potassium. As potassium-40 decays, it occasionally spits out a positron in the process. Antimatter-matter annihilations have the potential to release a huge amount of energy. A gram of antimatter could produce an explosion the size of a nuclear bomb. However, humans have only produced a minuscule amount of antimatter. If all the antimatter ever made by humans were annihilated at once, the energy produced wouldn't even be enough to boil a cup of tea. The problem lies in the efficiency and the cost of antimatter production and storage. Making 1 gram of antimatter would require approximately 25 million billion kilowatt hours of energy and cost over $1 million billion. PET scans use positrons to produce high-resolution images of the body. Positron-emitting radioactive isotopes are injected into the bloodstream, where they are naturally broken down, releasing positrons that meet electrons in the body and annihilate. The annihilations produce gamma rays that are used to construct the images. And with that, we come to the end of our presentation. Thank you.